So in that case, can we just do what we did yesterday?
Yeah. I think that's the backup anyway. But if we can try this,
But also we are getting late. It's 6:52.
so you're right. So Gayatri, shall we just do
Varni,
what we did?
Varni, I have
Yeah.
started live.
Okay.
Varni, I have started live, Varni.
Okay.
Varni, please, 1 minute. I have started.
Yeah. Gayatri, we can hear you.
We
I
can
have
hear you.
started. Varni, please listen to me. No, 1 minute.
Yeah. There's a lag. I can hear you.
Varni, can you hear me?
Yes, we can hear you. There may be a slight lag, but we can hear you clearly.
Okay, I have started live now. Okay.
Okay.
Hello.
Yes,
Yes.
Gayatri, we
Yeah.
can hear
I've
you.
started live now. Can I make? I'll try making Manigandan as host
Yes.
after.
Okay, try it.
Okay.
Yeah, I have done.
So we're all set.
Okay.
Varni, I've done
Mani?
that.
Okay,
Yeah,
Mani,
yeah.
can you check
Yes.
if you have your host, right?
Yeah, it's I am the
Okay.
host now.
And the streaming is still working? I
It
don't know if it is.
Yeah,
it
it's
mentions
working.
that
It's
it's
working.
live on YouTube.
Okay. And recording is also working, Gayatri?
That is working. That is working. I have
Okay.
not started the recording. I have
Okay.
that thing with me. I will start when the session starts.
Okay. You're recording it on Zoom or recorder or
Both,
both?
both, both, both.
Okay. Perfect. Yeah.
Yeah.
So,
Varni, I think the speaker has entered the room.
yeah. Hi, Dheeraj.
Hi, Varuni. Hi, I'm here.
Hi.
Yeah. Can you hear me
Hi.
Uh,
properly?
Yes, we
Okay.
can hear you well.
Let me turn on my video. You can see me as well, right?
Yes. Hi.
Hi, Dheeraj.
Hi.
do you want to try sharing your screen to make
Sure.
sure that works?
Mhm.
Uh, Manikandan, the students can be let in at this point. It's just 5 minutes for
Ah,
them. So whoever is waiting, keep admitting them.
Yeah.
yeah. There was one of them waiting, and I admitted them.
Okay, just one. Okay.
So, Sushmita, the other thing that happened this morning
Mm-hmm.
when we were testing it, there were like random people who were logging on because I think if you follow the Math Science channel, you get an update saying Math Science is live right now. So we may
Okay.
be getting random people from that also.
What do you mean we are getting random people right now? I hope people are coming to hear the talk right now.
Well, in the morning when people came,
Oh,
people were
oh.
like, "Oh, what is this subject he's showing?"
I see, I see,
And
I
so then
see.
Vishwanath had,
Oh, okay.
yeah,
Okay.
You can
yeah, we
see
can
my screen,
see,
right? Full screen?
yeah.
Yes, we can see your screen, Dheeraj.
Okay.
Okay, I'm gonna turn my mic as well.
Sushmita, shall we start or should we wait for more participants? I can't hear you actually.
You're on mute, Sushmita.
Oh, okay. I unmuted myself. Yeah, you can start. But once you start, keep paying attention to the new people who are coming because people come late.
Yeah, sure.
Okay.
So, good evening and welcome to everyone. I am Mani from IMSC Outreach. And so this is the second day of Facets, which is an annual mathematics lecture series organized by IMSC Outreach. And so today we have with us Dheeraj Kumar Hasra, who is a faculty member of Theoretical Science Department, Theoretical Physics Department in IMSC. And his talk is titled Codes, Computations and Constraints in Cosmology. And welcome to unmute yourself and ask any questions during the speech, or you could type in your queries in the chat box. And we'll also be having an informal Q&A session towards the end. So thank you everyone for coming over. And now over to Dheeraj for the talk.
Thanks, Mani. Thanks a lot. Okay, and
Sorry, excuse me.
hi.
Manigan, this is Gayatri. Can you please make me a host for a few minutes because I'm not able to record through Zoom.
Oh,
Sorry, sir. Sorry.
No problem. No issues.
yeah, I made you host, guys.
Can we wait for a few minutes before we start? So that this is, she finishes the resolving this problem and makes Manikandan the host again.
Yeah, she made me the host now. So.
Okay.
Give me a few
Yeah,
seconds.
Dheeraj.
I'll get a timer. So how long is the talk supposed to be?
7 to 8 minutes, 1 hour.
1 hour. Okay. So just okay. Then I don't need a timer. Just inform me around 50 minutes to 1 hour. Okay, around 45 minutes or so.
Sure.
Then I can be aware of the
Sure.
flow of the talk, and then I can make decisions
Sure.
to keep slides or describe more and things like that. Okay, thanks a lot. Thanks for inviting me as well. Okay, I'm going to talk about cosmology. Okay, so in cosmology, two things are extremely important. Is one is theory, and another part is the data from the observations. So these are the two pillars, big pillars in the foundation of cosmological principles or cosmological theories. So what we do is that from the data we try to shape up our theories. We try to understand our theories. We try to predict what is going to happen next, and this is how we do it. For example, let's start with a very simple problem, which is a terrestrial problem. Let's say, let's take an example of a train. Okay, a train that leaves Chennai and reaches, let's say, Vellore within 2 hours. All right, and in between it takes two stops into intermediate stations, and the data that you have is that when the train leaves Chennai, the source station, and when it reaches the destination station Vellore, and the time in between where it has stopped in the intermediate stations. So these are the four data points that you have, that you call observational data. And the fundamental theory that is there, that you are going to use in order to understand the problem, is the Newton's law. You know how Newton's law works, and you know that if there is an object moving with a velocity v and acceleration if, you know how you can get the distance, how you can measure the distance from that. So that is your fundamental theory. And the problem is that somebody asks you that what is the velocity of the train at different points in between the stations. All right. So you try to formulate your theory. You need to have some assumptions. Assumptions are that the train will have so the track is uniform or not, whether the train is going to have variable speeds in between, and when the train starts and when the train stops, the train accelerates or decelerates, and what is the probable acceleration and deceleration of the trains, and using these values. And of course there is another thing that will come in is the prior information. Prior means that a priori what you know about the train. You know that the train cannot have the lower speed than zero. It has a limiting speed of zero. It cannot have lesser speed than zero, and then it cannot also go more than 120 kilometers per hour. So these are the priors that are given. So using all this, you formulate your theory. You build up your theory with these assumptions and priors and the Newton's law as your fundamental theory, and you write a code to solve the theory. As you know that this is a complicated example, slightly complicated example compared to an uniformly speeding train, and you need a code to solve the theory, let's say. And then you have a statistical estimation. Statistical estimation says that how likely is your theory to match the data. So that is where we try to write some statistical estimators. That is called likelihood, which is what I said, that how likely is your theory to match the data. And you want to maximize the likelihood by varying your parameters. You have the theory, you have some parameters in your theory, and you vary the parameters, and you see how your theory matches with your data. And that's how you can understand what are the parameters in your theory. You can get constraints on your theory. Okay, so this is how things are done also in cosmology. There are also other ways to do things in cosmology. For example, uh, you can use the statistics and you can build up a methodology to do the reconstruction. That means that if you have the data, and by using some minimal assumptions, you, okay, let me get a point here. Okay, you try to trace back or reverse engineer your theory, your fundamental theory, or whatever behind whatever mechanism is behind that process that gives rise to this kind of data. Okay, so what we try to achieve with our with cosmology in our universe is that we try to talk about the origin and evolution of our universe, that when it started, and how it has evolved over time. And here we try to constrain our theories with the observational data. And here we talk about very large distances. So earthly distances are kilometers and more than that, but several thousands of kilometers. Earth to sun distances are some crores of kilometers, but we talk about much larger distances than that. So it is therefore it is useful to set some units. And as I said, centimeters and kilometers will work, but there will be many zeros. For example, if you go to crores of kilometers and beyond that, then you will need many number of zeros in order to address your theory or address your data. So how large distances we are talking about here is that, let's start with the solar system, our solar system family. As you can see, we are here and Earth is located here, and we say that from sun to Earth, whatever is the distance, we write it as 1 astronomical unit. So it is 149 million kilometers, and we say that this is 1 unit. Okay, and if you go farther and farther, you see the planets located at farther and farther distances. For example, Pluto is located at 39.5 astronomical units from us. And as you go further and further, you will know that the light travels in a finite speed. So light will take some time to reach you. For example, light will take some 5 hours of time to come from Pluto to you. So if Pluto is destroyed right now, you will know the news only after 5 hours. All right. Now, what is there in our neighborhood? So this is the Earth Sun system that is here, And if you go beyond, this is the star Alpha Centauri, which is there at nearly 10 to the 6 astronomical unit. So 6 zeros after 1. And light takes a huge amount of time to come from here to us. And also, as you can see, that we come to a new unit setup that where this astronomical unit is also having too many zeros. So we write another unit, we define another unit called light years. Okay, light years is that the distance that light travels within 1 year. Okay, and from the light year, so the light year, for example, 3.26 light years is nearly 2 lakhs astronomical unit. And from light year, you can also derive or also define 1 parsec. And 1 parsec is of the order of 3.26 light years, right? So we are going to use parsecs in most of our cases. So this is the picture of our Milky Way. The picture is taken from this European Southern Observatory, and this is the Andromeda galaxy. Okay, M81. And if we are talking about the distances, let's see how large the Andromeda galaxy is. So from the center to the edge, the radius of the Andromeda galaxy is of the order of 100,000 light years. So from the center, the light takes 100,000 years to reach at some planet or some star at the edge of the Andromeda galaxy, right? If we go to even larger distances, okay, we are talking about parsec, and if we go to megaparsec, that means 10 to the 6 parsecs, and gigaparsecs, we try to see how many stars or galaxies are there in our universe. We can do some survey. For example, this 2MASS was a survey in the 90s, I guess, and they have photographed the extended sources. There are point sources and extended sources. Extended sources are the sources that you can resolve. For example, if you are seeing a star, you cannot resolve the star with your telescope. You see it like a point, you call it point sources. And for example, sun, you can measure its distance just by looking at it. Measure its diameter or apparent diameter, whatever you call it. You can see some finite length in the sun's diameter that you can observe from Earth. So that you can call an extended source. For example, galaxies are extended sources. When you use a telescope and you look at the sky, you can resolve the galaxies, and they are extended sources. So there are many such extended sources. You can plot the extended sources as you have seen. One remarkable thing that you can notice from this plot is that the universe is same everywhere. Okay, so this is our galactic patch. So that you can see the Earth rotates. So the galaxy looks like this. So it is in a particular frame of reference that we have chosen. But apart from this part, if you take any finite part here, for example, you take a compass and make a circle, and you calculate the statistics. Statistics means that you calculate the number of this extended sources here, and you calculate the number of extended sources here. You will find that the numbers are very close to each other. You take here also, they will be very close to each other. But what happens if you take a very small place here, very small place here, and a very small place here? There the numbers will not match. As you can see that here you have many empty spaces, while here you can see too many stars or galaxies piled up here, right? So at small scales, when you are talking about small scales, the universe looks different. But when you go to larger scales, the universe looks the same. Okay. Also, if you take a direction here, take an arrow here, and draw one cone, and cone with an angle of theta. All right, and calculate the number of galaxies. Take some statistics and do it in this angle as well. The same theta angle you take, you will see the same number of galaxies. Okay, galaxies are extended sources, and this is a 2-degree freedom galaxy redshift survey. Here also you can see the same, that if you take any angle here and here, these are the galaxies, by the way, you will see the same properties, same numbers of galaxies in different directions and in different places. So this is called the homogeneity and isotropy. So this is something that builds our cosmological understanding. So this is one of the building blocks of our cosmological understanding. Okay, that our universe is same everywhere and same in every direction. So it is homogeneous, that is saying same everywhere and same in every direction. Whatever direction you are looking at, it should be same. Another example, if we are not talking about the stars, if you just calculate another statistics, for example, if you calculate the temperature of the universe, you put thermometers in different direction, you'll find an uniform temperature, which is 2.7255 Kelvin. This is called cosmic microwave background radiation. And where the photons, for example, I will explain as we progress in this talk. So cosmic microwave backgrounds are the photons that are streaming towards from the time it last interacted with matter. So when the temperature was very large, when the matter and radiation density were comparable, then the matter and radiation, so photon used to interact with matter a lot. Now, for example, there is no interaction between photon and matter, really none compared to the earlier days. For example, from sun, you can see that the light can come to you without being interacted with any other particles in between. So there is empty space in between, right? Cosmic microwave background is such a radiation. So the radiation that happened when the radiation dominated era, I'm going to explain that next, ends, and the photons became diluted. The radiation dilutes down, and the photon takes longer time to interact with the matter. So they come to us without being interacted with matter directly in a free streaming way. And if you calculate the temperature of the CMB background photons, cosmic microwave background photons, they will come to be 2.7255 Kelvin, and this is a uniform temperature. And the non-uniformity or the anisotropy, for example, this is isotropic, all right. What the difference, the delta T that is there, if you just take this temperature and you find that what is the difference in different direction, you will see that difference is nearly 1 part in a million. Okay, so this is a tremendously uniform temperature. Okay, I'm seeing, okay, great. Uh, Now, this is what I have learned, that properties of the universe, such as temperature, number counts, are similar in every direction and in every place. All right. And at sufficiently large scales, if you go to 100 megaparsec, now I'm giving you a number. Okay. At sufficiently large scales, at 100 megaparsecs or more, the statistics of the universe is very similar. Below that, you can see empty spaces somewhere and congested spaces or places filled with galaxies in the other direction. So the homogeneity and isotropy will not hold below this scale. So a very good lesson that we can learn from it is that where we are, there is nothing special about it. That means that we are not the center of our universe. So this is just as a common place as compared to any other place. All right. So that actually helps us in building some theory of the universe. So this is something that I would like to tell you, that density determines our destiny. Okay, what is the density of our universe at any point of time? That determines the destiny of the universe, or what happened before the before today in our universe. I talked about fundamental theories and assumptions. So for example, here the fundamental theory we are going to use is the general theory of relativity. So at very large masses and very fast objects, the Newton's theory doesn't work. So you need corrections or you need new theories. So here is the theory that works is the general theory of relativity given by Einstein. Okay, and general theory of relativity, in a very simple sense, relates the geometry of the space-time to the energy momentum contained within that space-time. All right. What it means is that whatever the energy is contained in one place, that is going to determine how you are going to measure the distances in that particular place. All right. So that means it actually controls the scale of the universe. All right. And it also gives you the evolution of the universe at any point of time. So the dominant component of the universe determines what its evolution is going to be. So homogeneity and isotropy dictates the form of the metric. Okay, metric means that the scale that with which you are basically measuring. For example, you know that if you are at point 0, let's say you are saying that you, in your reference frame, you are at the origin 0, 0 position, and there is some event happening from where you are receiving the signal, which is at r distance apart. So dr distance apart. So the distance will be dr square, right? So so this distance will be dr. So this is the metric that we are talking about. Now, if you have, for example, special, if you consider special theory of relativity, if you had any course on that, you will see that the time also come into that. Lorentz transformation is there, and there you can write some definition of the metric called ds square. Okay, so this is the interval between any two events, any two space-time events. Okay, so for example, in three-dimensional space, the distance is given by dr, while in a 3 plus 1 dimensional space, the interval, we are talking about interval here, not the distance directly. So here we talk about the interval, and the interval is given as ds. Okay, the d and the ds square is actually c dt square, the time interval, minus a square t dr square. Okay, so this can be formulated from the assumption of the homogeneity and isotropy. So that means that the universe, you can write any metric or any scale in the universe, any distance or any interval in the universe, using this one. All right, and this a square t contains the information about the time evolution of our universe. So this is the scale factor. This is something we call scale factor. All right, so yeah, scale factor, if it increases, that means that universe is expanding. Now, early observations already suggested that universe is expanding, and what is the typical speed of the expansion is that it says that h naught, I'm going to describe this quantity, is 70 kilometer per second per megaparsec. Okay, I already defined parsec. Megaparsec is 10 to the 6 times parsec. So two galaxies that are separated with each other by 1 megaparsec, they are going away from each other in different directions with a speed of 70 kilometers per second. So if the two galaxies are separated by 2 megaparsec, it will be 140 kilometers per second. It increases proportionally. All right. So this is a constraint. Okay, this is a constraint that we have arrived by using our observation and using our theory. All right. Now, if the universe is expanding from the energy momentum conservation and using the fact that it is expanding, you can say that the matter density, what if the matter density was, let's say, rho at certain point of time, if the universe expands, then the matter density will fall by 1 over r cube. It falls as a proportional to 1 over r cube. So it is very easy to understand that if there is a gas inside a volume, inside a ball of radius r square, let's say it's in a balloon, you inflate the balloon, you basically make the balloon larger, and you will see that you calculate the density of the balloon after some time. When it becomes larger, you will see that its density falls off as 1 over r cube, where r means the radius of the balloon, while radiation density falls as a function of 1 over r to the 4th. And dark energy density, we need that. Let's say I haven't defined dark energy, but something that is needed, dark energy density stays constant. Okay, so this is the standard model of our universe. So we know matter. We have seen matter in our universe. Everything is matter apart from the radiation that we look at. Radiation is the photons. So think that now the universe is expanding. What happened before? That means that universe was contracting. Okay, if you just take a video of our universe and run it backwards, you will see that whatever you are seeing now, the Earth to Sun distance, or the distance between two galaxies, it was smaller a few years ago, and a few millions years ago it was even smaller, and few billion years ago it was nearly zero. All right. So if that happens, then you can say that at some point of time, if there is an energy density which is constant, and if that is the fate, that is the state of our universe now, that if some constant energy density component is dominant in our universe at this time, before that there was matter density, and before that there was radiation density that was dominating in the universe. Just think now, just play the tape forward. Okay, means that initially the universe was radiation dominated. The size increased, radiation actually cooled faster. That means that radiation uh, uh, diluted faster than any other components, and then matter density came in. Okay, then that also got diluted. Then the thing that remains is the dark energy density, which has the energy density to be constant. All right, so which is the ruling our universe. So this is the picture of the universe: first radiation dominated, then matter dominated, then dark energy dominated. And I said that I talked about cosmic microwave background, right? So as I said, the radiation was the dominant component, then it became matter dominated component. In between that, when radiation was getting diluted, at some point of time, photons last interacted with matter. It didn't interact anymore after that. And from there, the photons free streams to us. That means that that is the place here. This is the place where photon starts streaming freely to us. That is the cosmic microwave background plane. Okay. All right. So this is going to be our notebook during this talk, and we are going to write down here whatever we learned. So we live in a homogeneous and isotropic universe, and our position is not special. And the universe is expanding, and the expansion has been driven by radiation, matter, and then the dark energy. All right. Now let's go to some equations. As I said that at some point of time, okay, so the general theory of relativity gives you the relation between geometry and the densities of the universe. And you have seen that this A is the scale factor that goes into the geometry. From the geometry, you can you can calculate some quantities, some tensors that are there. These are called Ricci tensors. So in the general theory of relativity, given any metric, you can calculate this type of tensors. And you can equate it to the right-hand side, which is the energy momentum tensor of the dominant component of the universe. All right. And then you can write down and derive what happens. For example, A dot by A, which is the derivative of your scale factor. That is how the universe is expanding. This is the H. Remember, I said that this defines how the two objects are getting separated from each other at a certain distance. Okay, so, situated at a certain distance. So this is the left-hand side. So which is the metric or the geometry of the space-time. Right-hand side has the rho. Rho means the energy density and pressure. So we get these two equations. These are called Friedmann equations. All right. And we try to solve these equations. And these are the two Friedmann-Robertson-Walker Friedmann equations that you can get from this Friedmann-Robertson-Walker metric. And this G, for example, is your is the gravitational constant that you get from Newton's theory of gravity, right? As you can see that everything is interlinked. Now, from there, you can derive certain quantities. What I'm trying to understand from here is that what is the age of the universe, for example. All right. So here we had the equations. We can make some variable change. We can write down these equations like this, where okay, just do not just ignore this quantity called z. Z is called redshift. Just think that the z is actually some transformation of time. So higher the z is, the earlier the time is. Okay. So at any point of time, the speed or this quantity h, this is called Hubble parameter. The Hubble parameter at any point of time was given as this one, where these omegas are the densities, okay, densities of the universe at a particular time. All right. So these are the omegas at today. And as you can see that if it is radiation at a particular time, it was given by omega r today divided by a to the 4, because it has decreased today. So omega m divided by a cube. Omega k, let's not talk about that right now. And omega lambda is the dark energy. Okay. So if somebody asks you that what is the age of the universe today, so you say that, okay, I'm going to integrate this equation and I'll try to find the integration. I will write the dt by dA. Okay, what is the, so A is, for example, this A dot is dA by dt. From that, you can just invert, you can get dt by dt dA, and then you integrate this dt, and here you can do the integration, and you integrate it from a time when the visible universe, observable universe, was zero. That time is called Big Bang, and from zero to at any point of time. So for example, if we normalize this A to 1 today, so you integrate this from 0 to 1, and if you integrate that, given this omega r, omega matter, and omega lambda, and this h naught value, you can get the age of the universe, how old our universe is. All right. So as I said that we have the theory now. We have certain parameters in the theory. We have certain assumptions which holds true with the observations. For example, the homogeneity and isotropy. With that, we have written the metric. We have equated with the fundamental equations of the Einstein's theory of relativity. Now we are going to solve this. We are going to make this simple integration. Very simple code. You write it in Python or any other code that you want. DTDA, and I just write the model name as lambda CDM, the standard model of the universe. It has some certain parameters, omega matter, omega lambda, and omega radiation, and the H naught value, the Hubble parameter today, and you just write whatever I have written here. All right, you are going to integrate that. Now you just plot the integrand. All right, the integrand as a function of scale factor. When it was zero Big Bang to today, the integrand looks like this for different values of omega matter. Omega matter, for example, what is the matter density of the universe? When omega matter is 1, that means that your universe is completely dominated by matter. There is no other component compared to matter density. When it is 0.1, that means your universe has 10% matter density. The rest part is dominated by something else, either by radiation or by dark energy. The question is that what values of the densities we should choose in order to integrate this integrand. So area under the curve is going to give you the age of the universe. We are going to calculate the area under the curve. That is the goal. So we need observations. So far we were talking about the theory part, assumption part. Now here it comes the observation. Let's take the observation of the star's death. So if a star explodes, not any star explodes in a two-star system, binary system, rotating star system, where one of them is a white dwarf, it actually gives you the type 1a supernova, IA supernova, sorry, it's called type IA supernova. And the important part here is that all this type 1a supernova has similar peak brightness. So they are like standard candles. That means that they, for example, these are like 100-watt bulbs. So you put the bulbs in different places, you can understand the distances. So if a bulb is located at certain point of distance, you calibrate with the bulb nearby, and you can say that what is the distance from where the other bulb is situated. Okay. So this is these are very useful observations that can give us the distances of the universe. So as I said, these are distance indicators. So what we do is that we observe the brightness of a supernova. We observe a lot of them at different directions and different distances. So that means that if we are talking about different distances, we are talking about different times as well, because the light takes time to come from variable time come from two distances, right? So divided by C. So and we get the matter and energy densities. We vary them. We vary the matter and dark energy density parameters, and find the expansion rate of the universe, find the acceleration of the universe. All right. So we had the A, the scale factor of the universe, speed of the universe, then the acceleration of the universe. What we are going to do is that we are going to plot the apparent brightness of the supernova, which is called distance modulus. These are the 580 supernova data that we are looking at. The vertical lines are the error bars. So every measurement has errors. So here also we have 580 data. So the central points are the, for example, central point here is the data point and observational data point, and these are the error bars. So it says that the value should be here plus minus this. Okay. Now you want to compare, we want to test our theory. How good is our theory? We make an estimator, which is called the likelihood. We are trying to optimize the likelihood. All right. First, let's give you a simple example. If we have zero matter, we have no matter component in the universe. You see, this is the theory that you are talking about. The theory gives us this as these points. The value should be like this. All right. And if you have, for example, you see that this theory is not able to fit the data properly. It is going above. While if you have zero dark energy, everything is matter, what happens is that the line goes below. Okay, so everything is matter, the line goes below. So it is not also a good fit to the data. So the theory is not likely to fit the data well. I take 30% of matter and 70% of dark energy. You see that theory fits the data beautifully. That gives you the understanding of the parameter estimation. Okay, so that gives you, if you calculate the acceleration of the universe, you will find the universe is accelerating right now. For that discovery, Rees, Perlmutter, and Smith got Nobel Prize in 2011. Now, the parameter estimation is a little bit complicated than that you need to get the error bars from that as well, because the data has error bars. So your estimated parameter will also have error bars, certain uncertainties. So you do a Markov chain Monte Carlo. You throw parameters, you just randomly pick parameters, and you get your theory. You get these lines that are fitting to the data. And from that lines, you calculate the likelihood, how likely they are going to fit the data. And from that, you can calculate the posterior probabilities. Okay, so this is the distribution. So this is the constraint. These are something called the constraints on the model parameter. So omega matter is the matter density, and W is the equational state of dark energy. Let's not take much attention to that, but this is something that the observation tells us just from one observation of the supernova. This says that the matter density is likely to fall between 0. The best fit is 0.317, between 0.317 plus 0.12 minus 0.082. Okay, so this is the bracket. So that means that this is 68% error bar. That means that with a 68% confidence, 68% probability, you can say that the matter density is contained between this region. All right. If you have several other observations, for example, if you I just showed you this one, so which is the supernova data. As you can see, the blue line is given as this. You can have also baryon and acoustic oscillation data. You can also have data from cosmic microwave background. You add all of them up, then you can get the constraints of the theory in a much better precision, okay, with a much better accuracy. So you see that here we are not able to constrain well. So you can see that here the contours were big, so the uncertainties were big. The bigger the contours, the bigger the uncertainties. But here we are able to constrain the universe with a very good precision. That means that your matter density is nearly 30% with an error bar here, which is very low. Let's not read of the error bar from here, but let's just get the numbers that our matter density is 30% and the rest is nearly 70% is the dark energy. Now we know what are the parameters. We again go to the Python code and we do the integration. We integrate this quantity and we calculate the age of the universe today is 13.79 or nearly 14 giga years. Okay, so this is the age of the universe today. All right. Now you can calculate the deceleration parameter. Okay, so I said that about acceleration. So deceleration is the opposite to acceleration. Now this parameter Q of Z means that if it is more than 0, that means that the universe is decelerating. If it is less than 0, that means that the universe is accelerating. And this Z is called redshift. As I said, this is a parameter. I'm not going to introduce much about this thing, but Z is a parameter. If Z becomes higher, that means we are going for the older times. Okay. Now, what happens when you have radiation? Initially, the universe was dominated by radiation. So universe was decelerating. Then the universe became dominated by matter. The universe is also decelerating, but with a lesser deceleration. Then the dark energy came, and we say that the universe is accelerating. So q of z becomes less than 0. Okay. So we learned here that the universe is presently in a state of accelerated expansion driven by dark energy and nearly 14 billion years, 14 billion years old. Probably some text will be cut because I think of the panel, of the Zoom panel, but I hope that you are able to see the slides. Okay. Now we know the evolution of a universe, radiation, matter, and dark energy, and this is the CMB part. Okay, this is the cosmic microwave background part. We can calculate the time here also from what is the radiation dominated epoch time till the radiation dominated epoch ends, when the photon last interacted with matter, is that 400,000 years, and the rest of the 14 billion years is here. Okay, nearly. So actually the total is 14 billion years. So 400,000 years were the radiation dominated epoch, or the time from the Big Bang when the radiation last interacted with matter. You can calculate from here to the two places, to the cosmic microwave background, and you can get the light cone. For example, light cone is something that gives you the causal connection. That means that anything between that has the time to interact between themselves. If the energy has this, okay, so if the speed is uh, the speed of light, so light could have interacted in this light cone, within this light cone, all right? And from here also you can draw backward light cones towards the Big Bang. Okay, so from where the universe has started, let's say our observable universe was 0. Now we know that every point here has a temperature of 2.7255 Kelvin, right? Brilliant. Everything is uniform. Now you see that if you actually draw the light cones, you will see that they didn't have time to interact. For example, this part could have interacted and given this part, and this part could have interacted, but this part and this part didn't interact before. Okay, so light could not reach from here to here. So if there was no interaction in the early universe, how come the universe had same temperature or have same temperature now? All right, so this is called the horizon problem. The cones do not match, light cones do not match. This is the problem of standard Big Bang cosmology. So this is a communication problem. So I have described it in this way, that think of a room with some high temperature in summer. You do not know the size of the room, and you know that someone has turned on air condition, and let's say the room has a temperature of 35 degrees Celsius, and you know that it takes time to uniformly make the entire room cooler. At some point of time, in 30 minutes, let's say, the room have a desired temperature of 22 degrees Celsius. Okay, but you don't wait for that time. You go in 5 minutes when you know that the room is not supposed to be at uniform temperature. So some part of the room will be at high temperature, some part of the room will be at lower temperature, because the AC air conditioner has just started operating in 5 minutes ago. And but you find the whole room, to your surprise, that the whole room has a uniform temperature of 22 degrees Celsius. How are you going to explain that? Because it is not physically possible, because the interaction didn't happen at a fixed pace. All right. Now, one possible way is that, as I said, you did not know the size of the room. You knew that the room had some, for example, had them 35 degrees Celsius, and you go there and find that the room is 22 degrees Celsius, right? So the possible solution is that the room was smaller. So a smaller room needs less time to cool. So air conditioner has started 35 degrees Celsius. The smaller room takes 5 minutes time to cool down to 22 degrees Celsius. It cooled down, and in the meantime, the size of the room has expanded exponentially, or expanded with a very high expansion rate. So the room was already at 5 minutes was at 22 degrees Celsius. It has expanded, and when you go there, you see that the room is 22 degrees Celsius. All right. So there was something that stretched the rooms apart in every direction, and the properties that were there got frozen in, and you see that the rooms were actually at every corner of the room is 22 degrees Celsius. Although if the room was this big, it could not have interacted between themselves, and the corners could not have the same temperature. So this is the pictorial representation of the problem. So this is what is happening, that the light cones were not able to interact. I say that there was an intermediate period called inflation between the Big Bang and the radiation dominated epoch, and between that time the universe enlarged a lot. So it exponentially and got enlarged. So the universe inflated. So the universe was there, it had the same temperature, light could have interacted. Then the universe expanded exponentially. The universe inflated. So the other point, all the points of the universe that were in causal contact with each other got inflated, had the same temperature, becomes the same temperature after the inflation period. So every part has expanded. All right. So that solves the problem, and this solution is called inflation. So this is the nearly exponential expansion of the universe driven by scalar field. There are many fields. For example, you know that there are matter fields, harmonic fields, photons, and there can be scalar fields as well, right? And this seeded the formation of structures also. So actually, inflation, when it solves this problem, also shows how to generate perturbations in the universe, and that perturbations actually leads to the formation of the large scale structure that we see the galaxies today. Their correlation and everything are the initial seeds were given by the inflation. All right. Now you need to have some predictive power of the inflation. So for example, this is a theory, right? It must have some predictive power that we can constrain some quantities. For example, it gives you a power spectrum. What power is there at what scales? So that has a tilt. Inflation says that it should have a particular tilt, and it also should produce primordial gravitational waves of certain magnitude. We have not detected primordial gravitational waves yet. We have detected gravitational waves from collapse, but not the primordial gravitational waves. But we have detected this spectral tilt with a very good accuracy, and it was the inflation was pioneered by Alexis Tarabinsky, Alan Guth, and Andre Linde, and many other scientists were there. For example, Slava Mukhanov Sasaki, who actually built the foundations of the inflations as well. So let's write it down. Before radiation domination, inflation drove the near exponential expansion of the universe. Now I talked about the uniform temperature, right? The 2.7255 Kelvin temperature all over the sky of the cosmic microwave background. Okay, Mani, how I'm doing with time?
It's been 50 minutes,
40
48
minutes.
minutes actually.
Okay.
48.
Okay. I have 12 minutes more. Okay. Fine.
Also, there are some questions in the chat. Would you like to address them now, or
how
we'll take
many
it
questions are
over
there?
Just one question actually.
Okay,
In
then
between the
let
chat.
me wait for a few minutes. Let me finish and
Yeah,
finish, and
sure.
then take the question. Because if there is only one question, we can take it at the end. Okay. So the universe has a fixed temperature of 2.725 Kelvin, and as I said, that it has some anisotropy. That the delta T. So if this is T0, the uniform temperature, you actually calculate the what is temperature in different direction, and you subtract this temperature. If you accurately calculate the temperature, then you see that there are some anisotropies which are 1 part in a million. Okay, so that is called cosmic microwave background anisotropy. So George Smoot and John Mather detected this. So first they had two components in this in that telescope. They sent a telescope to space around end of 1980s, and they got the result in the beginning of 1990s. And they found that the cosmic microwave background has a particular spectrum, the spectrum of black body, and also here the anisotropy looks like this. All right, you can calculate the power spectrum from here. All right, at what power is that there, at what scales? So for that, Smoot and Mather awarded Nobel Prize in 2006. Now let's talk about now we got the anisotropies, right? What we could do next is that we could build better telescopes to have better resolution. Just like your old TV, it has some standard definition, then high definition came, and then ultra high definition came today, right? I mean, this is the standard with the LED QLED TVs. So what happens is that there was another space telescope which is called WMAP, Wilkinson Microwave Anisotropic Probe. Mm, what did they do? I don't know why it's not playing. Yeah. You see that it observed the universe in a much better resolution and much better precision. So even the tiny components, tiny changes you can see here, tiny fluctuations with respect to the 2.725 Kelvin. All right. So this was your uniform temperature. You remove your uniform temperature. You see the anisotropy is like this, and then you make it better. You make it even see it in a better resolution, so you can see the power spectrum in a much better accuracy. How we do that? We send telescopes to space. The last space telescope in CMB was Planck, that was launched by ESA, European Space Agency. Before that, the Kobe and WMAP. That Kobe was sent by George Smoot and John Mather, and WMAP and the WMAP team that also sent the thing to space, send the satellite to space. They were all NASA mission. This is the European Space Agency mission. So you send the satellite to space in a Lagrange point L2, and you sweep the space and you look for the cosmic microwave background signal. That means you go to the microwave frequency and record the photon's temperature. And the red band that you are seeing is the band of our galaxy. Okay, so that cannot help you in getting. Okay, so that part is you have to mask when you are doing parameter estimation, when you're comparing the when you're using the data to constrain your theory. So it sweeps the whole sky, whole universe, and the cosmic microwave background map. When if you search in Google, you will find a beautiful picture like this. Okay, so these are the fluctuations. Okay, and this is the this is our galaxy, for example, in visible wavelengths. All right. So now you had this anisotropies. You can calculate the anisotropies at different angles, delta T1 and delta T2, that are separated by theta angles apart. And you can average over the sky and ask what is the power spectrum of this anisotropy. The power spectrum of the anisotropy, the data looks like this. The red dots are the data points, and these are the error bars. Now you have a model also. You have the model of the universe, which is the radiation, matter, dark energy. After that, after you solve the problem of horizon problem, that we have inflation, radiation, matter, dark energy. You calculate your theory, you compare it with the data. The best fit theory to the data looks like this. Okay, so this is a remarkable fit. That means that your standard model cosmology is actually remarkably addressing the data that you observe. I already talked about the constraints on the background parameters, the energy densities. Now I'm talking about the other component, the perturbation, that is coming from the inflation, right? So as I said, there are two things. One is two important parameters. One is the tilt. The tilt is called NS. Okay, here, sorry, this one is coming. Yeah, tilt is called NS, and the tensor to scalar ratio. This is the amplitude of the gravitational waves, let's say. Okay, primordial gravitational waves. We have not detected that, so you can see that we are not able to constrain that. So what this curve means, let me explain a bit more. Let's talk about one data. For example, Planck temperature and anisotropy. Let's say we talk about this gray band. All right, gray band looks like this. That means that the theory has to be your theory that is that is addressing the data has to be between this region. This and we do not know exactly what the theory is, the theory parameters are, and that is what your observation is saying. The observational error bar is like this, but you can see that there are many theories before that. For example, if the theory is here, what happened is that our detection is so precise, our detection of the cosmic microwave background is so precise that we have been able to rule out. So anything here, anything is there in the white area is already ruled out. So that means that those theories are not representing the universe, representing the data of the universe. For example, we have not been able to detect the primordial gravitational wave. Therefore, a tensor to scalar ratio of 0 also is within this error bar. That means that we have not detected. So if we detect that, it would look like a closed ellipse. You can see that it is an open ellipse, right? It is like this. If you add different data sets, the contours become smaller and smaller. That means that your detection becomes more precise. So here, if some data is some theory is here, you can say that the blue contour is actually throwing away that theory as well. It is not. It is rejecting that theory. All right. So, and we have already detected the tilt. The tilt is nearly 0.96, and it has said that if there is no tilt, uh, it has rejected that hypothesis or that theory with a very large confidence. That means that if you try to draw this ellipses, your confidence becomes bigger and bigger. So you can see that here, if you keep on drawing these ellipses, maybe around 8 ellipses, when the 8 ellipses are drawn, that will include this one value. Okay, that means that you are actually 8 sigma, 8 standard deviation confident that the one ns equal to 1 or the no tilt scenario, no tilt theory is rejected by 8 sigma. All right, so let's note it down. Cosmic microwave background observations detect the slope of the primordial fluctuation spectrum, which is a crucial prediction of inflation. We also can calculate the galaxies, right? As I said that initially I showed some picture of the galaxies. You can calculate the galaxies, you can calculate the power spectrum of the galaxies. And you can find, if you draw the power spectrum of the galaxies, the data, you find the same theory that fits the cosmic microwave background, fits the data from the galaxies as well, fits other data as well. So we have a theory that fits all the observations. Okay, so this is the lambda CDM theory or the standard model of cosmology. All right, so that is what is happening. So it says that the what it says is that the inflation that actually seeded the primordial fluctuations, quantum fluctuations, with a power spectrum that has a tilt of 0.96, that actually seeded the formation of this large scale structure, the galaxies and cluster of galaxies and their correlation, whatever we are seeing, that actually is the effect of the initial origin of the perturbations that you are seeing at the that you are your theory says at the beginning of your inflation. All right, so let's note it down. Initial fluctuations seeded the formation of the large scale structure. So this is the picture till now. All right, if you want to plot the picture of the universe, this looks like this. It started with the Big Bang. You had inflation, origin of fluctuations that they are that I said, origin of quantum fluctuation that gave rise to the structures. Then there was this radiation dominated epoch. Then this cosmic microwave background happened because the radiation cooled down. Then matter dominated epoch came in. Galaxies formed. These lines are galaxies, right? And then then there was the stars. If you cluster of galaxies, and then if you take one cluster of galaxies, if you zoom in, you find one galaxy. From one galaxy, you'll find a solar system. So from here we started, right? So you have seen that we have taken a full course of the cosmology from the Big Bang till today. Okay, so what now? What is there next? So we have not detected the primordial gravitational waves. So we do not know. We know that inflation happened. We really know that inflation happened, although it is not completely proved. So to completely pin it, we need need another prediction to be proved. That is the primordial gravitational waves. All right, the primordial gravitational wave, you need much better telescope. So this is something that we have proposed on behalf of scientists within India to ISRO, Indian Space Research Organization, and this is called our consortium collaboration is called CMB Bharat, and the telescope is called ECHO, exploring cosmic history and origin. And this is aimed to detect the primordial gravitational waves that will detect the energy scale of inflation. Uh, it can calculate, it can detect the neutrino mass also. It can weigh the neutrinos as well, the total mass of neutrinos. It can give a huge amount of information in the reionization era. I haven't talked about this. It can talk about the smaller scale physics as well. And we have proposed this as an ISRO. We proposed this to ISRO as an ISRO and European Space Agency joint mission. And these are the specification. It will be 2 tons. The mirror, it will have diameter of 4.4 meter, and it will have 2,400 detectors, and it can be launched with GSLV Mark III towards Sun Earth L2 orbit. and the PI is Tarun Sarodip of ISAR Pune, and it's called ECHO, as I said, and it will be a near ultimate CMB polarization survey. All right, and these are the working group that are working towards the mission, CMB Bharat, mission ECHO, in the CMB Bharat collaboration. So cosmological parameters, weak lensing, and few different other working groups are there. So we made a proposal. Our proposal contained the specifications of the satellite, and using the specification how we can constrain, how well we can constrain the physics that is not constrained now, how much better we can do. Okay. So another okay, so it is not approved yet, it is under review. Another survey uh, of which I am a part of, is the Euclid survey. It is already funded survey. Probably it will go to the space in 2022 or maybe 2023 because of the pandemic delay. It will measure the. It will go to the space and it will measure the shape and the spectra of galaxies and cluster within the last 10 billion years. Okay, and it will aim to constrain the geometry of the universe, nature of dark matter, dark energy, and lots of things. It will also test modifications to Einstein's theory of gravitation, whether we need modifications or not. It will also constrain primordial physics. As I said, the primordial physics is the same primordial physics that gave rise to the CMB fluctuations. Same thing applies to the galaxies. So if you can get the correlation of the galaxies, you can understand the primordial physics better as well, along with CMB. So to end, let me just tell you what my research is that I use CMB, cosmic microwave background, and the large scale structure. I gave you these two examples in order to understand inflation and reionization. And reionization I haven't talked about in this talk, but this is another important phase in the universe where when the galaxies form, they emitted light, and the neutral hydrogen atoms in the universe, uh, those hydrogen were became ionized from the energetic lights emitted by the luminous sources. So few works that I would like to just mention here, not describe. For example, whipped inflation, bingo. So this is a code. For example, as I have stressed many times that the codes are needed. So this is a code that calculates, that takes any model of inflation and gives you the power spectrum. Okay, so that's the bingo code. Reconstruction directly from the data, you can reconstruct theories called modify. I worked on this algorithm called modified Richardson algorithm in this collaboration. I've reconstructed reionization histories as well using different data, and with Euclid, I did some forecast, and I did some work on the primordial backward formation and stochastic background gravitational wave as well recently in these articles. So with that, I'd like to stop. Thanks a lot. So we can have questions now.
Thank you, Dheeraj. I think the participants can unmute themselves and ask any questions that they may have.
Sir, I had a question.
Mm-hmm.
Sir, while we were considering the inflation theory, we took the example of that room. So, my question is, while the inflation occurred in the room, won't it require much time to evenly spread the desired temperature, that is 22 degrees Celsius, throughout the space? Then again, it won't be affecting the age factor of the universe.
That is just that is okay. So let me go to the slide again. As I mentioned here in this slide, that caution, this analogy is not equivalent to inflation. It merely describes a causality problem. Causality problem means that uh, if you know that if the room is this big, if the air condition started, it will take 30 minutes. But you go there 5 minutes after the air condition is turned on, somebody called you and said that I have turned on the air condition, and you go there and you see that they are of uniform temperature 22 degrees Celsius. What I'm saying here is that actually the room was small. You were not given prior information about the room. You did not know what the room is, how big is the room. So you say that the room was at 35 degrees, a small room was 35 degrees Celsius, air condition turned on, it actually maybe it took 2 to 3 minutes or 5 minutes time to reach to 22 degrees Celsius, then the room has expanded. So that's how the causality that the particles could not have interacted, air particles could not have interacted and reached uniform temperature, that is solved here. Okay, so but this is just a pictorial representation. It doesn't give you the exact analogy of the inflation. So you should not confuse it directly with the inflation. But what you are asking is that what is the scale factor of the universe, right?
Yes, exactly. That is the question.
Yeah, so the scale factor of the universe is already, for example, you know, from the equations that I showed you, you can already calculate how much the uh, universe has expanded ever since. All right, what it does is that it says the universe was nearly a zero size, and the zero size became a huge size. Okay, now from the huge size, it is expanding. But from the zero size to huge size, this became nearly zero size to huge size. It took very small amount of time. The inflation happened a very small amount of time. Then after that, it starts increasing. Okay, so I'm just solving one part where the universe became this small to this big. So all things are taken into account inside the scale factors. We normalize the scale factor and take all these things into account. All right. So when we balance this equation, we basically balance the equation taking into account all these factors. Is it clear or no?
Yes, I got it right now.
Okay.
Dheeraj, actually, I had some questions sent to me privately. Can I maybe tell it to you? So it's
Sure.
from Suyog Gar. He asks actually, how do we know the time period between Big Bang and the CMB is 400,000 years?
Okay. Okay. Very simple. I write this integrand. Between Big Bang to radiation dominated epoch, there was no matter. I mean, matter was subdominant component. So, or just think that of the whole equation. All right. So you don't have to think about anything else. Just think about this equation. T is integral of A dA divided by this. You put everything in between. The equation will take care of itself. It will say that at some point of time, omega lambda was very small. For example, here, if you see, sorry, omega lambda was the same, omega matter was small, and omega radiation was the largest, because if A goes very small, this component is going to dominate. All right. Then you integrate from 0 to A. All right. You don't integrate from 0 to A. You integrate from the point 0 to a particular point where the particular point A, where the radiation stopped interacting with matter. All right, that A you can also calculate when the radiation and matter were of similar density. The energy density of the radiation and matter was similar, and radiation became cooler, and then it stopped interacting with matter. That particular scale factor A is of the order of 1 by 1000. Okay, 1 by 11,000 to be precise. So you integrate this equation from 0 to 1 by 11,000, sorry, 11, yeah, 1 by 1100, I'm sorry. If I have said 11,000, I'm sorry. It is 1 by 1100. So you integrate from 0 to 1 by 1100. And if you do that, if you just run this Python code anyway, and you say from 0 to 1, if 1 is today, you say 1 by 1100, you will get the age of the universe as 400,000 years. All right. Is it clear? Hello.
Yeah, I think the question has been. So we can have further questions now.
Yep.
Hello, sir. Good evening.
Good evening.
Sir, once I read that in the early stages, universe was expanding at speed greater than speed of light. So why doesn't it violate theory of relativity?
Oh, okay. Yeah. Okay. This question I get a lot, and this is a very interesting question. It is not at very early times, so you can think of this one, right? What I said here, uh, as of now, any two galaxies or any two objects in the universe that are separated by 1 megaparsec uh, from each other, they are receding, they are going apart from each other by 70 kilometer per second. Now think, if the universe, if you take 2 points that are separated by 10 gigaparsec, all right, 10 gigaparsec means 10 to the 4 megaparsec, all right. That means then you put the number of zeros here, you will find that it is like 700,000 kilometer per second. Two objects that are separated by 10 gigaparsec are going away from each other at a speed of 700,000 or 7 lakh kilometer per second. That means that it is, and what is the speed of light? It is 3 lakh kilometer per second, nearly 3 lakh kilometer, 300,000 kilometer per second, nearly the double of the speed of light. It doesn't violate causality. The only reason for that is that these two, causality says that if there are two events happen, if there are two events, for example, at place A to and then at a place B, the information, how fast the information is going to come from A to B. So if the two regions are separated by 10 gigaparsec apart, no information can reach from A to B. They can go away from each other. All right. Think of a square or think of a cube. All right. Think of a cube and you think that what is the volume of the cube? It is a cube, right? If the one arm of the cube is of size A. Now you say that you say what is the yeah, let's put it in this way. How fast the what is the okay, yeah, take the example of a cube and say that your cube is expanding. All right, you ask a question that at any point of time, how what is the how fast the volume of the cube is expanding. Now, what you will find is that it needs much less time, much less speed for the 2 points to go from each other, lesser speed than the speed of light, in order to get a greater speed with which the volume is expanding. Okay, so the main idea is that if the 2 points get separated from each other, that does not mean that causality is violated. If any information is transmitted from one place and reaches to another place faster than the speed of light, that means that the causality is violated. All right. So this is the interval between two events. All right. So it is these two events are causally separated from each other. They are not causally interacting. So that is what is happening. That every point of the universe is going away from each other. So the larger points are going even faster at a faster speed. All right. Any other questions? Mani?
There are no other questions in chat, so.
Right. So let me just stop screen sharing.
So we will end it here and have an informal session right now so that people can talk to you after the recording is done.
Sure.
So thank you, Dheeraj, for sharing all those fascinating theories and insights about the universe. I'm sure everyone had a great time listening to you. So now participants can informally converse with Dheeraj about their questions. So the recording has been stopped and you can feel free to ask your questions right now.
Sir,
Yes.
sir, this was a very nice talk, and I learned many things from this. I am Chandan Kumar. Yeah,
Hi, Chandan. Hi.
sir. So my question, this talk raises many question in my mind. Many question in the sense that, like you said that the 10, giga years observations are with us, giga years observation, like some with some error in them. So how these observations were taken? Like if we consider our lifespan, it's 70 year or 50 year, then how these observations were taken? And you want to propose Euclid project in which 10 billion years observation will be taken. So till now, what are the ways we take the observations?
Okay, very interesting question. You should have asked this in the recording session as well. It would have been having really great discussion. Um, we cannot, uh, okay, we cannot record the evolution of the universe directly. For example, if you record the evolution of certain things, that a train is going or whatever, you record something, you get its evolution. But when you talk about the universe, it is actually a bit more simpler. It is not more complex actually, because if you take a photo of the sun, as I said in my first slide and my first one, 3 or 4 slides, I think I showed that the solar system, right?
Yes, sir.
Pluto.
Yes.
When you're talking about Pluto, you take a photo of the Pluto. You are taking the photo of 5 years older Pluto.
Yes.
If you take a star, if you are taking the 5 hours older Pluto. If you take the photo of a star or a galaxy that is separated several light years away, that means you are talking about several years older, several years younger version of that galaxy or star. If you talk about a star that is, or the galaxy is located very far from us, then you are actually talking about a star that is 1 giga-year older than us, or 10 giga. So you take the supernova or the starburst, so the star has already died 10 giga-years ago. All right, its light is reaching to us. Why its light is reaching to us? It was very energetic. That's why it was not getting absorbed by anything, and then it started, and the space is open. It starts steaming freely, and it comes to you. And when you are seeing it, that supernova is not there. It has, the star has already destroyed 10 giga-years ago, but you are seeing its seeing its image now. All right, so whatever is there outside, you are seeing its image now. So you take the full sky image, you will see from few years old stars. Okay, not few years old stars, because there is no star that is that close to us. Few years old galaxies cannot happen, because galaxies are much separated, much farther separated from us. So you will see that the galaxies that are few megaparsec away from us to the few gigaparsec away from us. So the older the distance, the larger the distance, the younger the star's image that you are seeing. So in one photo, you are getting the full evolution of the universe from the 10 giga years till today. In the CMB also, CMB, you are seeing the whole universe when it was 400,000 years old. Then you are getting some evolution from there that is coming to us freely. That is a very important thing. So yeah, it is just by looking at, just not taking a video. For example, Earth is going to be destroyed at some point of time, and
Yes.
Earth was not even there a few giga years ago, right?
Yes.
It is not possible us to capture all the
Information.
any of the videos, but we can get everything by just taking the photos. the dynamics of the universe is encoded in the photos.
Thank you, sir. Thank you, sir.
Welcome. Any other questions? Mani, any other question?
I think we can, and there are no questions from the chat too. I think we can wrap it up.
Okay.
I don't think anyone has. So thanks again for coming and
Thanks a
giving
lot.
us this talk.
Okay. Bye.
Varuni, I'm stopping.